What's up, folks? Welcome back to the next lecture in vector calculus. Today I'm going to show you this problem. How do you find the distance between two planes? Here's our first plane, 3x minus y plus 2z minus 6 is 0. And our second plane is 6x minus 2y plus 4z plus 4 is 0. I'm hydrated. Are you ready? Let's go. Folks, welcome to vector calculus. Alright, folks, you're back. How do we do this problem? Well, the first thing you want to really do is draw a picture. You knew that was coming, didn't you? Well, that's what I always do. I draw a picture. Now, the first plane here is 3x minus y plus 2z minus 6. And here's the second plane. Do you notice something similar? If you don't, let me write it out for you, alright? Here's our first plane. 3x. Oh, what do you know? I settled with the bad marker. Oh, geez. Alright, I got the better one. Let's see if this one works. So we've got 3x minus y plus 2z, and all of that equals 6. Okay? And our second plane is 6x minus 2y plus 4z is equal to negative 4. Okay? Now, do you see the similarity? If you multiply the first equation by 2, you'll get the exact same coefficients as in the second equation. Only your d value, your value on the other hand side, the constant value is going to be different. But except for that, all the other things, all the coefficients are the same. Okay, are all the same. So, what does that tell us about this? Well, when you have two coefficients, when you have all the coefficients as the same, you're talking about two parallel planes. Alright, so these two planes that we want to find the distance between, they're actually parallel. So they're going to look something like that. Right? Here's my first plane. Here's my first plane. And here's my second plane. Okay, they're parallel. So far as we're concerned, they are the same plane, just separated by some constant. And we want to know what that constant is. We want to know the distance between these two guys. So how can we find that? Well, to find the distance between two planes, we can use what we learned in the past lecture. In the last lecture, we learned how to find the distance between a point and a plane. Same thing here. Just grab a point on one of this plane, grab a point on this plane, connect these two guys, and you're going to get a vector. Project that vector onto the normal vector of the plane you want to find the distance from. And what are you going to end up with? You're going to end up with the distance between these two guys. Okay, that right there, that projection, the projection of vector A onto the normal vector is going to give us the distance between our two planes. Alright, with that being said, let's go ahead and get started. How do we find these 2 points? Well, let's first and foremost get a point on our first plane. Okay, so let me shift this way over. How are we going to get a point on our first plane? Okay, well, this is our first plane. How do we get a point on that? Well, just find a point you like. It looks like 2, 0, 0 works for this one. So I'll settle with 2, 0, 0. Maybe you're asking, why does 2, 0, 0 work? Well, just plug in the points, right? Plug in the coordinates. Instead of x, put in 2. Instead of y, put in 0. And instead of z, put in 0. Do you get 12 on the right hand side? Well, 6 times 2 is 12. 2 times 0 is 0. And 4 times 0 is 0. And so yes, you do end up with 12. 12 equals 12, and we're good to go, folks. How about the second equation? Well, once again, try a point that fits. I see that negative 1 fits for z. So 0, 0, negative 1 looks good to me. And of course, I can always check that, right? Instead of x, I can put 0. instead of y I can put 0, and instead of z I can put -1. So plus 4 times -1. And will I get -4 on the right hand side? Well, 6 times 0 is 0, 2 times 0 is 0, 4 times -1 is -4, and so yes indeed, I do get -4 is -4, and so the point is indeed on the plane. Alright, I'm halfway there, folks. I'm halfway there. I got a point on both of my planes. So how's that gonna look like in a picture? Well, let me draw the picture out for you really nicely. So here is my first plane. I don't know if you see that clearly, but there's my first plane. And here's my second plane. Here's my second plane. These are almost like the, those nets at the tennis courts, right? All right, I gotta do a 360 so my mic doesn't flip off. So here's our first point. What's the coordinates of our first point? 2, not, as I like to call it, 2, 0, 0. And what are the coordinates of our second point? 0, 0, -1. So here, for example, is our second point, and its coordinates are 0, 0, -1. Alright, now what do we do with these 2 points if we want to find the distance between our 2 parallel planes? Well, we can connect these 2 points with some vector. What's that vector going to be? We'll just subtract the components, or rather the coordinates of our points. 0 minus 2 is -2, 0 minus 0 is 0, and -1 minus 0 is -1. So that's the vector connecting our 2 points. That's all fair and square, Jimmy hair. But we're going to project that vector onto the normal vector, onto this normal vector of our plane. And what is that normal vector? Well, just peel off the coefficients of your plane. So both of the planes have the same coefficients, namely 6x minus 2y plus 4z equals some constant, and so that tells us automatically the components of this normal vector, and that's going to be 6 comma -2 comma 4. Okay, well, now if I go ahead and project this vector onto this normal vector, I'm going to get the distance between my 2 parallel planes. And so what's that projection going to look like? Well, I can write it as follows. Projection of this vector, let's call it A, onto this vector, let's call it N for normal. So the projection of my A vector onto my normal vector is going to be what? Well, remember the projection formula tells us the projection of A onto N is the dot product of my 2 vectors divided by the magnitude of N. Alright, well now, hopefully you can fill in the gaps here. What is the dot product going to be on top? The dot product on top is simply going to be the dot product of these 2 vectors. Okay, well, it seems like it's time to put this guy down here, and so we can continue our calculations here. What's my vector A? Well, it's -2, 0, -1. Take the dot product of that with N, my normal vector, which is 6, -2, and 4. Divide all of that by the magnitude of my normal vector, which is going to be what? Well, it's going to be 6 squared plus -2 squared plus -4 squared, or rather, sorry, 4 squared. And so, if we just go ahead and simplify this, what's the projection of our vector E onto N going to be? Well, it's going to be -2 times 6 plus 0 times -2 plus -1 times 4. I always say -4, I don't know why. And divide all of that by the magnitude of our normal vector, okay, which is going to be square root of 6 squared, which is 36, plus -2 squared, which is 4, and 4 squared, which is 16. And so what are we left with? Well, we're left with the projection of A onto N, which is going to be what? Well, here I've got -12 plus 0 minus 4. Divide all of that by the square root of 36 plus 4 is 40, plus 16 is 56. And so what are we left with for the projection of A onto B? Well, we're left with the distance between our two parallel planes. So the projection of A onto N, also known as the distance between our two planes, is going to be negative 16 over the square root of 56. And that, ladies and gentlemen, is going to be the distance between our two parallel planes. And of course, distance is positive, so you can make this positive as you wish. Okay? And that, ladies and gentlemen, is how you find the distance between two parallel planes. Before we cap it off with that, let me just go ahead and give you one final picture. So here's our two parallel planes, and we just found the distance between them is going to be given by the projection of A onto N, and of course we just found what the actual scalar value of that is, which is 16 over root 56. And that's all you need to find the distance between two parallel planes. Alright folks, thanks for watching this lecture. We'll check you out in the next one.
Embedded plus MKO plus scaffolding equals learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.